Lesson 6-1 on values of basic trig functions. So here's some bullet points on the introduction to trig functions that we're going to be looking over in chapter 6. Trigonometry is one of the most useful branches of mathematics and is very applicable in science. Trigonometry is based on angles, distances, and triangles, specifically the relationship between an interior angle in a triangle and the ratio of its side lengths. The Pythagorean theorem allows us to find the length of any side of a right triangle if we know the two other sides. It is a powerful tool because it helps us find one side of a triangle based on a reference angle and a corresponding side. It allows us to find interior angles based on two sides of the triangle. Despite the diversity of the applications of trig functions, the entire subject can be boiled down to the three basic trig functions and their reciprocals. So see here in this box are the three basic trig functions that have been provided for you: the sine, cosine, and the tangent function, all of which you covered in geometry. But let's look over these and refresh because it is been kind of a while since you last saw this topic. So we are given here an illustration of a right triangle, and we all know that a right triangle will always contain a 90-degree angle, and these two angles that are left over, they are going to be the sum of 90 degrees because, as we know, all angles of a triangle have to add up to be 180. So if this one's 90 degrees, the two others have to sum to be a 90-degree angle. Have to sum up to a 90-degree value. Those two angles are always going to be acute. In other words, they're going to be less than 90 degrees. Now, when you are looking at a right triangle, there are going to be opportunities for you to either stand on one of these acute angles, or you will be directed to stand at an acute angle. In this particular problem, they're asking us to look at certain ratios from the angle A perspective. So what I need you to do is I want you to visualize yourself standing at angle A as instructed. Okay, so we're going to draw a little stick figure here. So you're standing here at angle A. So if I asked you to find the sine of angle A, what I'm asking you to do is to stand at angle A, and I need you to find the length of the opposite side, and I need you to put that in the numerator and then find the length of the hypotenuse side. Opposite side from when you are standing is always going to be directly across from you, the leg directly across from you. Now, I said the word leg. What I want you to remember about legs is that legs are always going to be, let me change color here a second. Legs are always going to be the two side lengths of a right triangle that form the 90-degree angle. So I'm going to make these really bold here. So that and this right here are the legs of this right triangle, because these two legs join to form the 90-degree angle. Okay, so when I ask you to look for the side opposite, it's going to be the leg that is across from you, and then the hypotenuse. Let's bold this in red. The hypotenuse side is always going to be that third side, of course. That's not the leg, but notice that the hypotenuse is always going to be the longest side, and it is directly across from this 90-degree angle. Okay. Notice also in a right triangle, the hypotenuse is the slanted side, whereas the legs form a 90-degree angle. They're going to be a horizontal and vertical line in a certain orientation, obviously. Adjacent. I want you to notice adjacent always means, from your point of reference, it's the leg right next to you. The nearest leg is always going to be the adjacent leg. So here, if you need to remind yourself, adjacent is always, ooh, that's not spelt right. Adjacent is always going to be the nearest leg from where you're standing, and opposite is going to be the leg across from you, okay, from where you are standing. So for instance, I'm going to erase this all here a second. If I were standing right here at angle B, right? So I'm going to change this to angle B, and I asked you to find the opposite side. Well, this time, if you're standing right here, notice that, again, the leg is still this one, because it's the side that is going to form the 90-degree angles, the two sides that form the 90-degree angle. This time, the leg opposite from you would be that one, okay? So it really is important for you to understand where you are standing to determine which is your adjacent leg and which one's your opposite leg, okay? Okay, now, in pre-calc, we introduced to you 3 more trig ratios, and we call these the reciprocal trig ratios. So flip your page over, and you're going to notice that cosecant A is actually the reciprocal. You know what? Let's write it on this side, actually. Cosecant A is actually the reciprocal of the sine A function, okay? And we're using the letter A as from the previous page, opposite over hypotenuse, okay? So sine is opposite over hypotenuse, but notice that cosecant, CSC stands for cosecant, is going to be the reverse, the reciprocal. So the O goes downstairs and the H goes upstairs, so it's a hypotenuse over opposite. Secant, its reciprocal, comes from cosine of a given angle. Cosine is A over H. Cosecant is H over A. And then as far as cotangent, well, that is the reciprocal of tangent of an angle. And originally it was O over A. And when you flip it, it becomes cotangent, which is A over O. So once you know the length, the ratios of a sine function, you will always know what the cosecant is, because you just take that ratio and you take the reciprocal. All right. So these are the 6 trig functions that you're going to work with a lot this chapter. So let's do these 3 problems, and then you can dive right into your homework. The first practice problem, we're going to keep it real simple. If you are given 2 side lengths of a right triangle, find the length of the third side. I like to encourage students to please first identify what are your lengths of your legs and what is the hypotenuse. So as told before, the legs are always going to be the sides that form the 90-degree angle. So I'm making this really bold so it will pop out. And so I am going to make sure I understand that this here is a leg and this here is a leg. And the side across from that 90-degree angle is my hypotenuse, okay? We do know that the Pythagorean theorem, let's write this down, the Pythagorean, oh, forgot the N, the Pythagorean theorem is something that students tend to remember quite readily, and that's a squared plus b squared equals to c squared. But what I need you to remember is what exactly A, B, and C stand for. Well, A and B are always going to be the length of your legs. No particular order, by the way. So whatever the leg length is, you're going to square it, plus whatever the other leg squared it And that's always going to equal whatever the length of the hypotenuse is and square it. So in our particular problem, let us substitute. We have a 4 plus, we don't have another leg, so we can call it b squared. And the hypotenuse, we have it to be 8. You are going to simplify. 4 to the second power is 16. 8 to the second power is 64. Once I subtract 16 on both sides, let's go over here. That leaves me with b squared equals 248. In order to solve for b, which is the leg length that I'm looking for, I will have to square root to get rid of that squared and solve for b, which is the leg, and that's going to be square root of 48. What I want you to realize, though, in the instructions is they want us to write everything in simplest radical form. This indeed is a radical, but is it in simplest radical form? Well, what you're going to do is do some tree factoring. So I'm going to come over here a little bit more again. You're going to take the square root number that you got. Square root of 48 is not like if it was square root of 36, you would just tell me it's a 6. Or square root of 25, you would just tell me 5, and so forth. These are perfect squares. Square root of 48 is not a perfect square. So what I'm going to do is create a factor tree. Now you can also divide out the highest perfect square. Some students do it that way, and it's a lot faster. But I'm going to use the factor tree since this is the most widely used approach by students. So 48, well, the prime factor of 2 will go into 48 24 times. 2 times 24 is 48. 2 is a prime number, so I'm not going to touch that anymore. 2 also goes into 24 12 times, and I'm going to keep factoring. 2 goes into 12 6 times, and 2 goes into 6 3 times. Okay, so for the most part, you're always dividing by the prime factor 2, 3, or 5 to start breaking down your factor tree. I'm going to circle the pairs. I have a pair of 2's, which made, 2 times 2 is 4. I have another pair of 2's, and then I have a 3 that doesn't have any pairs. Well, remember I'm taking the square root of all these values. So the square root of this first oval, 2 times 2, the square root of 4 is just a 2, right? And the square, let me put a dot there. The square root of 4 here is also just, is also just a 2. And that 3, well, nothing's happening to it because it doesn't have a pair. So my b is going to equal to the 2 times 2 that came out, which makes a 4. And inside the radical, the 3 was left all alone. So you would type as a final length for that missing leg to be 4 square root of 3. And you are done. Okay. Moving on to the second to last problem. So in this particular problem, they're telling us that they're going to give us a ratio, that the cosine of the angle that we're standing at, the cosine of A is 7 over square root of 85. They're telling us that the angle A is in quadrant number 1, and they want us to find the exact value of cotangent of A. The value of cotangent A must be in simple, let me fix my sleeve here, simple radical form. And it also stipulated that the denominator must be a rational number. Okay, so what does it mean to have an angle in quadrant 1? What does it mean to have that? Okay, so what I want you to do is over here on the left, I want you to draw an X and a Y axis. All right, quadrant 1 is this quadrant. Quadrant 2 is this quadrant. 3, and 4. All right. So when they ask you guys to draw a triangle, a right triangle in a quadrant, for instance, in quadrant 1, it would look something like this. I'm going to start like at the origin. I'm going to draw out the hypotenuse and then draw down the legs. Okay. So here is a triangle in quadrant 1. Here is my 90-degree angle, by the way. Okay. If I wanted a quadrant, an angle in quadrant, let's say 3, I would draw it. Let me pick another color. I would draw it like this. Here's one for angle 3. Did I even pick another color? I think I picked 10 again. Oh well. If I wanted one in quadrant 2, it would look like this. I'm drawing them at different sizes just to prove a point. And if it was in quadrant 3, it would look something like this. Okay. So a little shifted a little bit further up. So what I want you guys to understand is, for now, there we go. Well, goodness gracious. There we go. For now, all the angles that you are going to work with are going to be in quadrant 1 for this section, okay? Only in quadrant 1. So do not worry about quadrants 2, 3, and 4 for now, but I wanted to go ahead and draw those out so you can see sort of like the bow tie effect of what those triangles look like when they are located in certain quadrants, okay? So let's undo these that I've drawn and let's just focus on this one. Now, they told us in this problem that the cosine of the angle A is 7 over square root of 85. So angle A is going to be one of the acute angles. It's either going to be that one or that one. We are going to choose the acute angle A to be this one. Why? Because it's right there by the origin. So always use the one at the origin. Okay, so there's angle A. And they're saying when you're standing at angle A, goodness, this corrective pen sometimes is annoying. I'm trying to make this A a little bit more pronounced so that you guys see it. Okay, so if you're standing at angle A, they said the ratio of the sides is 7 over square root of 85. So what you need to make sure that you remember is that cosine stands for adjacent over hypotenuse, A over H, okay? Adjacent over hypotenuse. So if I'm standing right here, I know that this and this are my legs. So my adjacent leg is going to be the leg that is closer to me. So that, in this case, is going to be this leg is a 7. My hypotenuse is square root of 85. And the opposite side, I don't know what it is. This opposite side, I don't know what the length is. This is my adjacent, okay? And this is my hypotenuse. So sometimes labeling it will also help, okay? So they asked us to find, what was it? Cotangent of A. So let's write cotangent of A. So they gave us cosine of A. We're asked to find cotangent of A. Now cotangent of A is what? It is going to be A over O. In other words, adjacent over opposite. Now, luckily for us, one of the length of the sides we already know, that's a 7. So I'm just going to put a 7 right there. Okay. The opposite, I have no idea what it is. It's blank. It's a missing side length. So just like we did earlier, we are going to find the missing leg. Find the missing leg, which is the opposite leg, by using Pythagorean theorem. Leg squared plus missing leg squared equals square root of 85. squared. This is going to be 49. We're going to call the leg b again, b squared equals, and the square root of 85 squared will just be 85. I will have to subtract 49 on both sides. And when I do, I'm going to end up with b squared equals to 36. Thankfully, 36 is a perfect square. So when I take the square root of 36, it's just going to be a 6, and I'm not going to have to do any factor or tree with this one. I needed to find the opposite length, so now I have enough information. The cotangent of A is 7 over the length I just found. And this is what you would type into Delta Math and hit enter and submit. Is this written with a rational denominator? Absolutely. 6 is definitely a rational denominator, so we can use it. It's not a radical either, so it's an acceptable answer. So in practice problem 3, I'm going to give you an example where a denominator is not going to be rational, and how do you fix that? So since we know our angle is in quadrant 1, okay, remember I said in this homework set, all the angles you guys are given is going to be from the quadrant 1 perspective. So you don't have to draw 4 quadrants since you already know what the triangle is going to look like. So let me draw a little sketch. So first quadrant triangle looks like this. We know that this right here is going to be capital A. And I know this already is the OPP. The ADJ is this leg. And I know this one here is my hypotenuse. So what was given to me? Well, the secant A is the square root of 13 over 3. So this information helps me label the length of my sides. First, secant means what? It means, let's see, trying to remember, secant's cosine, which is adjacent over hypotenuse, so this is going to be hypotenuse over the adjacent. Okay, hypotenuse over the adjacent. So, label the hypotenuse with a square root of 13. The adjacent is going to be labeled with a 3, and here we are again. It's completely coincidental. We're looking for the opposite length again. So, leg squared, my first leg. Let's go ahead and look for that missing side, okay? The leg that we know is 3 squared plus question mark squared, so let's call it B, equals square root of 13, which is the hypotenuse squared. 3 times 3 is 9, and square root of 13 times square root of 13 will just be a 3. I am going to divide, not divide, sorry, 9, subtract it on both sides. So b to the second power is going to give me a 4, and yay for us, 4 is a perfect square. So b is going to be 2. The length of our missing side is a 2. So let's come over here and write next to the question mark, it's a 2. They want us to find the sine of A. The sine of A is the opposite over the hypotenuse. Well, what number is the length of the of the opposite? The sine A is going to equals the 2. What is the length of the hypotenuse? A square root of 13. So here's an example where this is a correct answer value, but because they want us to make sure that we only provided answers with rational denominators, this is not going to work because that denominator is a radical. and we want a rational. So if you have forgotten what to do to be able to manipulate this fraction into becoming a fraction where the denominator is rational, here's what you do. You are going to multiply by the radical you are trying to get rid of. But if you multiply the denominator by that radical, you must also multiply the numerator by that radical. Make sure that radical is in simplified format. The square root of 13, when you do the factor tree for square root of 13, 2 doesn't go in, 3 doesn't go in, 5 doesn't go in. The only one that goes in is 1 times 13, and you can't go any further than that. So make sure your radicals are fully simplified, okay? So again, this one it is. So 2 times square root of 13 for the numerator is just 2 square root of 13. And square root of 13 times square root of 13 is just plain old 13. Why? Because if I were to rewrite this, square root of 13 times square root of 13, that's like saying square root of 13 all squared. And we all know that a square root and a square will undo itself. So that's why you're left with a whole number 13, which is rational. Okay, this one turns out to be rational. So this here is going to be an approved answer. So you would type that out. Okay. I have had one last thing where students have popularly asked this. If they ended up with the length of a side that was something like this, the 3 square root of 2. And let's say this was the length of a leg, and you had to square it in the Pythagorean theorem. How do you find the value of 3 square root of 2 all squared? Well, that just means you're going to take the 3 and you're going to square it, and you're going to multiply it also by the squared of square root of 2. So in a way, you are sharing the exponent to both terms in the inside. 3 to the second power is a 9. The square root raised to a second power is just the number inside that radical. So this will end up equaling 18. Okay? So if you come across a situation where you have a number outside of the radical and the whole thing's being squared, make sure each one of those numbers are raised to the second power. And that's it. That is lesson 6.1. Thank you so much for watching.